Okay, let's start our seminar or webinar, and let's talk a little about SVM, support vector machines, and risk bounds for them. What do we need to know? First of all, we want to skip some info. First of all, we want to discuss the following situation. Sometimes we want not only to split our elements offset by two regions with positive labels and negative ones. Sometimes we want to find the best separating half space hyperplane to split the points in the best way in some doubt. Of course, the best way, it means that we want to find the best margin that which divide the highest distance, which divide the space of positive ones and negative ones. Okay, so we have some geometric understanding of the situation. We know how to define the hyperplane in some space. We know that it can be rewritten like scalar product that equals to 0. I think is it clear that we can define the hyperplane in this way? I hope. Okay, so using with knowledge and using knowledge of finding of the projection of the vector to another vector, we can say the following thing. We want to find the best possible vector W, so that it will define the best hyperplane that will divide our positive labeled elements and negative labeled. So it can be rewritten as a kind of complicated problem. Like we can say the following thing: but we have some set of or list of x with labels y, and we want to rescale with that's our like the pairs x y is our usual training sample, and we want to find the minimum of this expression to find the margin, the distance between which separates regions of pluses and of minuses. So after rescaling, we can rewrite this task in this form, like we have such values of W that gives us metric that equals to 1, like W divided by norm of W. So after that we will have the following margin. Okay, so after that we want to find the minimum value of vector of W, minimum norm of it, square of norm of it, so that these equalities hold. That means that our points are classified correctly. So it's well known that this task is written in convex type. That's a convex type problem. We know that we have convex objective function, this one, and we know conditions from which define convex set. So we can find an optimal point in some very good point, good enough, in polynomial time. So this task can be solved efficiently. Also, we know that it has unique correct solution because all the convex optimization problems with strictly convex objective always have a unique solution. Okay. So what do we want to? What does support vector means? It means that we have some set of axes. We have this set of conditions. And first of all, we want to say that the best value of W can be rewritten as a scalar product of beta and x, like in some doubt, scalar product. So we, you know what, it can be called scalar product because we have
Sorry, y it is
label
0
of x1.
y it 0 or 1
Yeah,
or 1 or
that's a good question because it looks like if we had
minus
none,
1 1.
yes, looks like we need to use 1 or minus 1 in this case.
Okay.
Unfortunately, I have not so much. I haven't much enough experience in machine learning, so I need some time to think about it before giving an answer. Yes. So okay, we have a lemma that vector w lies in the span of x, of set of x, because if we split w into parts, like in a sum of part from the span and like plus part from the orthogonal, how can it be дополнение, how can we pronounce it in English? Addition? Sounds terrible. Okay, maybe you understand what I mean. You know that if we have some part of W that from orthogonal addition, when in this case it won't influence on the inequalities because it will give us a sum of zero, only zero summaries. But at the same time, it will increase the square of norm of vector v. So what means that we can skip the part, this orthogonal part of vector v, and we will only minimize the objective. So we want to say that when we have some, the main idea is that if we have some training sample, when we can find the best value of vector w, which defines the margin, the half space, and the best margin, only using these vectors x. Some of them which have non-zero multiplier, because some of these x, some of these x's can give us, can be achieved like the, I don't know, like the linear combination of other x's, and they can have no influence on the vector w because we are not linearly independent. So such set of x's that can give us the best hyperplane are called support vectors. Okay, everything is okay, I think. I'm afraid that it's a kind of complicated topic to pronounce it in such fast way. So I hope that it's close to okay. So what can we say? That we know from the previous lectures, we got that there are some measures of sample complexity, such like Weiss dimension, and in its terms, the sample complexity can be computed in this time, and can be achieved in this time. And we know that for any proper consistent learner, we need this time of computing to achieve this number of elements in this training sample to achieve good bounds, and blah blah blah. But we want to find some way to bound sample complexity with no dependence on YC dimension of our set of functions, or maybe with no difference on the number of dimensions. Okay, but the previous our talk was dedicated to realizable setting, because we had an assumption that we can split all our training sample elements by using the hyperplane. But sometimes, of course, we have no such possibility. For example, right here, suppose that we moved some point, some red point here and some blue point here. So now we have no possibility to find the best hyperplane, but our past hyperplane with white one still splits our training sample very good. What does it mean? But now we live in agnostic setting, but our hyperplanes can't split everything perfectly. But now we have an idea to find good enough hyperplane that splits good enough our training sample, for example. So here we can see some kind of optimization of our task. In the previous part we had hard margin. That means that it was strict value of W that splits our sample very good. But now we have another task. We can optimize it for agnostic setting in this way. We can add sums. We can add with sum for the objective, and we can change a little our, how can I say, we can change little our conditions. But now we can with some vectors, with some for some vectors, we can have none of the strict inequality that with product is higher than 1. We can make it a little more less, if it's possible to pronounce, to say this way. So it means that we can we give possibility, we allow for our hyperplane, this set of conditions tells us that we allow our hyperplanes to not to split some of the elements, some elements. So that's what we want to do. For example, we can use hinge loss, and we can define xi with 1 numbers. Like you can see that what does it mean? What can we say about the hinge loss? It equals to 0 if we classified our point correctly, and it equals to 2 if we classified it incorrectly. So it looks like that we can optimize with value of W, so that we have penalty for misclassified elements. Okay, so we try to do with some low as it possible. Yes, and we have penalty for misclassified vectors. So we don't try just to find the best W. Okay, it's a still problem that can be computed in an appropriate time, polynomial time. So also you can see that even using replacing of normal vector v with some convex function f from f normal v, we will achieve the convex optimization problem, and we can compute it in appropriate time, and so on, blah blah blah. So we have some optimization of our task for realizable setting for the agnostic setting. So, but we have a question: Does it work good? It's it's a normal question, I think, that you can expect. Uh, okay, in the previous chapters, in the previous lectures, we had some close to equality, some similarity, that agnostic sample complexity is proportional to the VC dimension in square, and VC dimension is usually close to the number of parameters, if you remember. So now we given a margin assumption on P, so P, as you know, it's a measure, it's a probability over X product X times Y. But now we have assumption that a large area between positive and negative points has small probability. In this case, we can get that agnostic sample complexity is close to the square of this fraction. So we try to get an understanding why we can bound the agnostic sample complexity without number, with no dependence on number of parameters or number of features. So we'll need to introduce lots of definitions, lots of inequalities and other terrible things. For example, we need to introduce one more risk. If you remember, we had very high amount of risks: usual risk, empirical risk, Rademacher risk, and so on, so on, so on. Rademacher complexity, which was written with R like risk. So we'll dive in the flow of the definitions with the closed out, but we'll try to do the best not to die till the end. I don't know how to pronounce it. Okay, let's talk about the regression task. Like we have regression to interval 0, 1, and we have some measure of the x and y, and we have this loss function. As you can see, it gives us 0 if our answer of our classifier is correct, and it can be more than 1. That's normal. One question: do you understand why we need this minimum function here? We make a regression over interval 0, 1, so why can't we write just modulo of our prediction and real value? What was the question?
Yes, it's clear.
Okay, but to be honest, it was really hard to hear you. I hope that it's clear for everybody. But I want to say that was because when we make classifiers, we can, if you remember, we had such conditions, how to say it, свойства. Please help me.
Property.
Property. Thank you. We have such property like consistency. That means that our classifier produces labels from space Y. We have, and right now we haven't said that our classifiers are consistent, so we can produce labels like 2, 3, or 1 million, which doesn't belong to the segment 0, 1. So that's why we need minimum function. Okay, after that we can introduce one more values of risks, like usual risk and empirical risk of a regression function f. We have some penalty function, some loss function L, and we can introduce, first of all, empirical risk minimizer. Empirical risk in this way, like something average of the mistakes on some list Z. And we have some risk. We have risk without empirical. That's an expectation of the mistake, of misclassifying. Expectation of value of loss function. Okay, and we want to get some risk bound. We can, like in the previous chapters, we want to bound the usual risk using empirical risk on some training sample. We had some terrible inequalities with and it's really hard to pronounce them, not to not to understand. Like we know that we had some way to bound the probability of bound the value of some function. Like I hope that you understand the main idea of this inequality. That's like we want to bound the value of some function, usually loss function, using average mistake on a training sample and some measure of complexity of your set of functions. That's like Rademacher complexity. If you remember, we had with one thing that was with one definition of Rademacher complexity. So maybe it's worth to open this page in the other tab, because I always forget the definition. And also we have some term which depends on the correctness of our prediction. It's like how high will be our insurance when we build good enough classifier. We had some terrible contraction lemma. I don't remember where it was, in the lecture or in the seminar, blah blah blah. But the main idea is that empirical risk could be bounded for composition of functions, can be bounded with Lipschitz constant multiplied by the empirical risk of the function f on the set of functions f. It looks like it's a Rademacher complexity. Rademacher complexity of list z. It's really complicated to pronounce, sorry. Okay, so we had some infinite number of inequalities. I'm not sure what you want to talk on about all of them, but the only important thing I want to say that in a pure way we can't compute we can't apply this contraction lemma in the case of half space classifications, because if we have with one loss function, for example, but indicator of correct classifying, when in this case our function will be not Lipschitz. Do you understand what does it mean, Lipschitz function? I hope that yes. So we can apply contraction lemma, so we can give good estimation and so on. Okay, so this happens because if we talk about something like binary classification, or like for -1 and 1, or for 0 and 1, and so on, when in this case we can when we have half space classifications, we can move x a little and we can change the value of loss function significantly. Like we change for 1 divided by million, and we will change the value from -1 to 1. So it will so this function can be Lipschitz like. So we have first idea is to say that if we have some margin, when in this case, in this tube, in this margin tube, we can define we can use not simple binary classification loss function, but with one loss function, which will be first of all continuous, and even 1 divided by r Lipschitz. So if we will use this one loss function, when after changing x for little, we won't have possibility to change the value of y significantly in infinite amount of times, not more than for 1 divided by r. So in this case we can use construction lemma, like to bound the real risk by the empirical risk. So and we start making some terrible inequalities, blah blah blah, like we want to apply terrible inequalities from the previous lectures. In our case, I'm not sure what you want to talk about all of these computations, but you can just remember that we have some terrible inequalities. You can say something if you want to talk about them, but I expect that you don't want to talk about them. Okay, so, also let's add some restrictions, some that usually used in practical situations. Like sometimes, usually we search for the best W, but not in all the possible. But we are searching for the best W not in the whole space R in power n. But usually we want to use vectors vectors W with bounded metric, with bounded length. So usually we use this type, set of functions. Like we want to find the best hyperplane, but such that vector W will have bounded norm. No, not metric, sorry, no. In this case, we can bound the empirical complexity. We can bound the empirical. Sorry, 1 second. I want to open it again before my eyes, because I always forget the notions used. There are too much of them. Where was it? Complexity. Where it was defined. Okay, sorry, it looks like it hasn't been defined yet. Okay, sorry. Let's turn back. Okay, we can define we can bound the average Riemann complexity for the list with this term, with this sum. It looks terrible, but the best way is just to agree with it and with it. Or if you want, you can read some books like Morphy books and so on. So there is an idea that we can connect the idea of Hull spaces with the idea of kernels. Like we can look on this, we can use this one kernel, yes, such that it equals to phi x multiplied by phi x with hat, with tilde. And we can compute that in this case our terrible Riemann average complexity will be bound with one terrible expression. So it looks great. Okay, one more way to compute. So, and like both inequality, we can see that. Now let's fix some number r, some number rho. I'm not sure how it can be pronounced. I think that rho is the best way. we know that if we have axis from some R sphere with the center at the 0, 0, when in this case we can bound the risk of signum of f with this one terrible sum. Like, look, that we it's worth mention. It's worth to mention that we have that we use functions f that belongs to the space of bounded norms of vector w. So in this case, when x's are bounded and our vectors w are bounded too, when in this case we can bound the risk of misclassification with some. It looks terrible, I agree, but I can't help you. There is no idea how can I help you in this case. Blah blah blah. We have some more inequalities, and also we introduce the idea of hinge loss and comparison of it with margin risk. Look, suppose assume that we have these two functions like margin loss and hinge loss. What's the problem of hinge loss? It gives us infinitely high values of. It can give us infinitely high values if in the case of incorrect misclassification. So we have an idea to apply minimum of 1 and something that close for minimum of 1 and hinge loss for the optimizing of loss function. I'm not sure how it can be pronounced even in Russian. When in this case we can make some terrible bounds on the margin risk, blah blah blah, and so on, some terrible inequalities which are hard to be pronounced. And at the end we can conclude the remarks. What was the main goal of the lecture? First of all, we tried to find some way to bound the risk for half space classification that won't depend on n but will depend to the margin size. So now in the terms also we can see in this formula we can see that it can be bound with the real risk can be bound with the least complexity, but the empirical risk using empirical risk and using some term this term that depends on the how can it be said what depends on the restrictions for axis and for functions f, and this term is connected to the possibility of how can we pronounce of overfitting, because sometimes because why do we need these terms? Why do we need these bounds? Like if you remember when we were talking about the soft margin, why did we need these extra penalties? Because we wanted to give possibility to build such hyperplane which will misclassify some points, and secondary we were afraid of overfitting, because we could find some extremely complicated value of vector w such that won't work in all the possible cases with good probability, because it will be overfitted for some maybe strange list. It depends on the specific of training sample. So blah blah blah. Also, we want to say that our way to solve task of soft margin will have possibility to give us not structural risk minimizer, but it will be good enough classifier at the end. But and also it's mentioned to it's not worth to mention that it's easier to tune a value of C. If you remember, that was parameter that dedicated to overfitting terms. So I'm not sure what it was pretty to listen, but I hope that it was in some way useful for you. So if we have none questions, or if you don't know what to ask, then we can move to the seminar. Okay? Okay. Especially if there are any students right now. Okay. I'm glad to see that all of you are still here. Okay, let's move to the tasks. We have the first one, as you can see, is dedicated to our terrible inequalities. We want to say that in the case of bounded axis and in the case of bounded vectors W, and in the case of this loss function, when we can bound the risk of our function with empirical risk, with this one term, and multiplied by 2 plus square of logarithm. As you can see, it's really close to this inequality. Yes? Let's try to prove this inequality. I think that the best way to start is to apply as to look at this inequality. What can we say about it? How it can be applied? It's really complicated to discuss this task, I'm afraid, because we need to write high amount of inequalities and to feel the difference between applying them. Also, I want to mention that I have no solution of this task, so we will try to solve it here. Look, what bounds do we have? We know that the space Y is a segment of B minus of B plus of B. We know that norm of axis is bounded by B. We know that norm of W is bounded by R, sorry. We know that our class of functions are bounded by B. And we have this one mistake function, loss function. That's the condition of our test. And we know that we have.
In formula from lecture, f
One second, I just want to rewrite it because I think it will be convenient to you to look. Okay, I will use this value of delta for this symbol because I'm not sure how to type it. I don't know how to type it. Square of rho top plus. Okay. Am I right? Yeah, I lost double. Okay. Now I'm ready to listen to you.
f it's parameterization family of function, and delta it's parameter.
Delta is parameter.
What is delta?
What is
Delta.
delta? Delta is a bound measure for the delta is bound measure for the value of w. Like, oh,
In our case, it's
it's b.
it's b. Okay.
Yes, let's say it off. Functions.
Okay.
Okay, I add. It's impossible to remember all the definitions. But it took a lot of time for me to remember at least the uh, to remember the majority of them. Okay, we know that delta beautiful equals to b in our case. Also,
X let just about 2 maybe in second line
and
on the left. No. On the desk or on the left part. Uh, 2 line.
to you have possibility to talk in Russian. I want to
Там не
mention
должно быть r в квадрате во второй строчке.
about R square. To be honest, I'm not sure because I'm afraid that there are some typos in this task. In this task.
Okay.
So or maybe we just need to find some appropriate value of R to build it correctly. Look, right now, of course, we can easily say that using the theorem from the lecture, but we can bound value of risk in this way. But look, what part of the condition we doesn't touch? We even doesn't touch. What's the difference in for the case of applying of this lemma and in with our case? What's the difference? We haven't looked on a part of the condition. Which one? I want to say that we haven't already touched with one part that we use with value of this type of loss function. Look, what do we know about the risk? What does it mean? You can see that here we have an inequality for the risk where we applied some signum function. But right now we're interested in the in the pure risk. And let's remember how do we define the risk. I don't remember, where was it? Please help me to find it. There did we, yes, this one. Risk is the mathematical expectation of the loss function. Okay? We want to bound the mathematical expectation of loss function. So right now, this inequality is really good, but the problem is that here we use something like signum classification, like binary, 0 or 1. But here we have some much more complicated loss function.
And signum always will be positive.
Signum will be always positive. Why? Sometimes signum is
Loss
negative.
function, loss function positive.
Because loss function is positive, and we defined loss function is always positive. Okay, maybe you're quite right. Okay, I won't argue with you. Because, for example, right here we decided to use. Okay, yes, it will be a non-negative expression. Okay, I agree with you. It looks like that we need to compute the it looks like that we need to compute these bounds using something more complicated, not with one inequality, which was given for signum from f, which gives us 0 in the case of correct classification and 1 in the case of incorrect classification. Yes, but we want to compute in more complicated situation when we have some which is close to definition, when we know for all the possible set of functions, measures, and so on, we have this one inequality. Okay, it looks like that we need to apply this one inequalities, or maybe with one inequality. That looks like more. But it looks like with this inequality, it looks like more like when what we need. Sorry for my terrible English. Because here we have a pure risk of f. Okay, it looks like that we need to bound Rademacher complexity. But we need to compute something that looks like Rademacher complexity of our set of functions. But I'm a bit afraid of it. Something like the mathematical expectation of this thing. But it sounds terrible. I'm not sure that that's a thing we really need to do on the seminar, because it looks really complicated. One second, please. And what if we need? Okay, to be honest, I'm afraid that it will take a lot of time looking for a correct inequality we need to work with. So I suggest you to maybe to skip this task, because at least I have answers for other tasks, and in other case we will have no time to discuss them. But at least we can solve these tasks on the seminar, so maybe it's worth talk about them. What do you think? Do you agree?
Sure.
Okay, yes, well, that's great. For example, we have some task that doesn't depend on very deep understanding of the situation. For example, like with one, we are suggested to compute the empirical margin risk for some appropriate, some concrete values of parameters. Okay, let's revise the definition of empirical risk. Where is it? I always lose its definition. Where was it? Ah, okay, loss functions at the beginning of the loss function topic. Okay, we have some value of empirical risk of regression function. Like, let's write it on the desk, on the board. Desk. Z f that equals to 1 divided by power of z sum of x y. We have with, I'm afraid yes, it won't be seen, so I will skip the head on the r. We want to compute it in the case of in the case that we apply some threshold functions with a concrete value of t, yes, and we have some training sample with blue ones are zeros and red ones are 1. And we have margin risk with r with rho equals to with 1 values, and we want to compute these multiplications. Okay, let's do it. What can we say in this case? Maybe it's worth to rewrite. I will be pleased if you will help me to rewrite this line, because it's really complicated to -5 -3 -2 1. Yes, and we want to compute, for example, it won't be very beautiful table, but at least what we have else. Look,
Sorry, what is
as I understand, that's the size of our sample. We used m for the length of sample, like, or like, okay, let's revise, but I'm afraid that I'm not sure. But it looks, yes, that's the same size of sample. Like, you know, the training sample is sampled from p in power of m. That means that length of our training sample is m. Okay, we know that it equals, like in our case, that it equals to 7. Okay, let's think what we can say in this case? Like, look, we have, as you can see, we have we have classifier. First of all, we know that we have some classifier that threshold function for 0. So with one classifier. Yes, and we have margin of 0, 5. What can we compute? How can we compute this expression? Let's think about it. Like our Z is a training sample, if you understand. So if we want to compute this expression, what we can do? First of all, we can rewrite it like 1 divided by m, and we need to compute the values of loss function. I think that in this task we want to use value of loss with one value of loss function. But to be honest, I'm not sure, because if you can see, there is no concrete loss function in our condition of the task. Okay, let's fix some loss function.
Sorry, what is rho?
Rho is the margin, is a size of distance with no penalty. Like is a tube in which we are not sure how to classify this element. Sorry, 1 second, I will return in a minute. Sorry. If you remember, we were talking about what's the main idea of margin? Is some tube from the it's some tube over the how can it be pronounced? Over the half space, our hyperplane that splits the space. So that in this tube, our elements can have high possibility of incorrect classification, and when they skip the size of this margin
So
distance.
in our case, ft it's mean.
Yes, it looks like we need.
Okay.
Yes, it looks like it was a bad idea to write L, and it's better to use phi. Oh, I just need to write it again. Phi rho. It equals to 0 in the case of how many tabs I have. The value of margin is like level of our insurance that we classify correctly. Some distance of high insurance. Yes, we are suggested to compute this one expression for all the possible x and y. I'm just not sure. 1 second, I need some time to be sure that I wrote it correctly. Yes, it's better to. Okay, I don't think we need it. Okay, what can we say in our situation. But how can we compute? Like what give us our what our classifier will give us for this element, for example. We know, as you understand, we can divide all the set in our case when we have classifier with t equals to 0. When we have set of classification, here we classify using 0, here we classify using 1, and we have margin of 0, 5. There we are not sure, but we have some lack of insurance of correct classification. What can we say? For example, when we will compute this sum for this element, in this case, it's easy to see that we have correct classification. Yes. I'm not sure. It looks like we need to use x here. So we're correct. Yes, we're correct. Computing. What will we have using what we will get when we will compute sum for this element? In this case, we can see that our value of function phi. Yes. What will we have? We know that this element is rated far from margin, so, and it's classified correctly, so we will get 0. Okay or not okay?
Okay.
Okay.
And same thing will happen with this free one, with these free blue ones.
We do mistake only 0.1.
Yes, but only problem will be with the 0.1. What will we get for it? In this case, it will be stated far from margin. One second, please. I just want to. Yes. Yes. In this case, we can. It will be value of it will be equal to 1. You know that our x, like the value of classifier, will give us 1 because it's situated in the right side, but at the same time the real value of element will be equal to -1, so the product will be -1, so we'll get 1 in this, so we will get only 1 in this sum. Okay.
So sum equal 1 divided by 7.
Yes, it looks like it will be. Okay. Sum will be equal to 1 divided by 7. Yes, and we were asked to compute the value multiplied by n. So as you can see, our table will be, you know, but this term will be equal
Okay.
by 1 divided by 7. So it will be multiplied by n. So we'll get 1 in this case. Okay.
Okay.
So I'm not sure, but it's really interesting, but we can repeat it several times. Maybe it doesn't work our time, so maybe you can compute it manually without my help, without my how to say, участие, without me. Okay, so maybe we can compute it one more time for this value of t and r. Let's do it, and after that we will move to other tasks. Okay, and let's consider the situation when we have classifier with minus for 1.5. What do you think? What will be the value of our multiplication? What do you expect from this value? Any ideas? Let's participate in this seminar. I feel very lonely.
It's okay that t divided by rho will be negative.
It won't. You won't say that with situation
No,
won't happen.
1 minus t divided by rho.
No.
Okay. No.
I won't say that all the points will be classified correctly. So even
Yeah.
using the measure. Okay. So in this case we'll get only zeros in our sum. So for example, in this case we'll achieve 0. So if you want, you can compute this table till the end. But I think it's worth to move in some other lens. I'm not sure which one task do we need. Okay, let's move to the third one, for example, and let's compute. Let's approximate one more risk again. We on the lecture we had some margin-based generalization bounds with blah 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 blah. But now we are suggested to compute not a hinge loss, but something that close to square of hinge loss. Okay, like to apply the loss function in some other way. Look, if you remember, we were using this one loss function for some inequalities in the lecture. Now we are suggested to apply this one inequality, this one loss function, and we are suggested to estimate the risk. Okay, I think that sounds terrible. It's better to just to read the solution because we have no time to solve it from the beginning. So what do you think about the reading and discussing the solution? I hope that everything is agreed with it. Okay?
Okay.
Okay, we can apply one of the lemma from the lecture so that for all the possible classes of of functions, for the 0-1 segment reduction. How can I say it? It's so simple word, and again, regression, of course. But for the 0-1 segment regression, we can write with one inequality. The mathematical expectation of G is bounded by this blah 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 blah. And we want to say that they had some boundaries for the margin risk, for a simple margin risk. So let's find it. We bounded bounds for the margin risk, like with one inequality. Yes, and now we are suggested to say that we just need to mention that in the case of quadratic function, it won't be 1 divided by r Lipschitz, but it will be 2 divided by r Lipschitz. Okay, not okay? We just want to say that we have some terrible inequality with one. As you can see, it's really close to the inequality we want to it's really close to inequality we want to prove, as you can see. Yes? we want to apply with inequality for usual hinge loss, but now we have but we used only the Lipschitz constant from the construction construction lemma, which was equal to 1 divided by r. Like here you can see that Vr is 1 divided by rho Lipschitz. But now in the quadratic case, we will get 2 divided by r, 2 divided by rho Lipschitz function. So we'll get the same inequality, but only with constant 2, not without, but with only with constant constant 4 in the skeletal. So that's the only idea in the task. I'm not sure, but it's really interesting, to be honest. Okay, at least you, soon you will get the solutions from Brune, and it will be, maybe it will be more easy to understand. And one more interesting task. So that we have some space of functions f, which contains the zero function, and we want to say that if we use bounded norms of w, when in this case, when we can estimate the value of complexity of bounded one, or the complexity of linear space of these functions by complexity of the set of the functions multiplied by some constant. Okay, it sounds terrible again, as I think, and it really needs a lot of time just to understand the condition of the task. So maybe it's worth to open the solution again, especially in the case when we have only 4 minutes till the end of our seminar-like event. Especially in our case, we had low chances to invent the solution from the start yourself, because it's really something that looks really complicated. But there is some simple idea of solving, but let's discuss it. There are 2 solutions, but let's revise the more beautiful one. Like what the set of the functions do we discuss? We said we have all the possible functions from f, and now we want to build all the possible linear combinations using bounded set of weights. Okay, I think that you understood what space of functions do we use. Okay, I hope that you understood this expression. Okay, in this case we can mention, understand that our set lin B can be rewritten as the union of all the the possible convex holes of f united with minus f multiplied by b for all the b from 0 till the big B. Okay, do you agree with this equality? Okay, I hope that you agree. But now it sounds like the auditory was lost. Okay. We have some simple lemma with complexity of union can be of such union can be bounded with the b multiplied by the complexity of a set of functions. To be honest, it looks like some natural inequality. It's a kind of strange set of functions, this one. But as you can see, that in some case, the complexity of G is kind of linear. If you remember, it was one of the results from the previous seminar and from the previous lecture. But Rademacher complexity has something close to linearity. For example, so we have a proof of this inequality such that if you it's easy to see that Rademacher complexity, if you remember the definition of it, let's revise. It's a mathematical expectation of supremums of some product, of some scalar products divided by m and so on, blah blah blah, and using the fact that our set G contains zero function, we can easily say that the supremum that all these supremums that we want to compute for the Rademacher complexity are always unless zero or positive, non-negative at least. So in this case, we can say the following. We can state some statement. For example, such that supremum of this multiplication of this combination, for when we iterate for all the possible values of b and for all the possible values of b, it equals to supremum with the big B. I think it's easy to understand why this equality holds. But on the previous seminar, we had fact that when we proved some statement, maybe you remember it, that if we have supremum for modular of some set of functions, when it can be bounded by supremums from of f and the supremum of minus f, so it can be bound and they equal one to each other, so the supremum of modular can be bounded with two Rademacher complexities. So we can apply this inequality again, and we can say first of all we proved this inequality, and after that, using the fact that G can be written a linear space of F can be written as the union of the sets of this type, we can achieve the constant 2 and get the finishing inequality. I'm not sure what it sounds at least normally, but unfortunately that's everything I can say, what I can do. So I suggest you to finish the close to seminar event, and see you next week.